Good morning, everybody. Welcome to the second session of the last day. Now I have the pleasure to introduce Leonardo Poveda. He's coming from IME in Sao Paulo, and he's going to talk about localized harmonic characteristic basic functions for MsFEM.
Thank you. It's a pleasure to be here in the IMPA. It's my first presentation. Okay. We're going to talk about localized harmonic characteristic functions for multi-scale finite element methods. This works is in collaboration with Juan Galvis from Universidad Nacional de Colombia and Victor Calo from Coutinho University. Okay, first, the basic problem we consider. We focus the problem in elliptic problems with discontinuous coefficients. Basically, we understand the solution of elliptic problems with discontinuous coefficient with the large jumps. These problems are maybe in porous media or composite materials. Anyway, we consider the pressure equation for fluid flow in the main porous media. For example, metamaterials, composite materials. For example, temperature equation for heat flow in composite materials. Okay, effective properties of composite materials. This is the talk. Okay, the example for this talk, we consider a 2D pressure equation on the Darcy law, given the subset of R2, F in this condition, G for the boundary condition. We can find U, the D to R, such that this equation. Okay. Here, the kappa of X is represent the permeability of the porous media in this case. Okay, we consider one kind of domain. The kind of domain is, for example, in the region white is take a value 1. In this case is low conductivity in this part of the domain, and the color parts is in this part occurred high conductivity inside in these inclusions, but the terms eta is very higher, the high conductivity coefficients. Okay, for example, in the physical phenomena, we consider a highly dense distribution of these inclusions. In the physical problems, for example, this paper, we take effective thermal conductivity for these dispersed materials, for example. This is the example. Okay, we focus again the elliptic problems. We consider the PDE in this form. Again, kappa is the coefficient, the high contrast coefficient, and okay, we denote the D is a disjoint union of this domain. First, the background domain is we denote D0 union of other parts of the inclusions. Okay, this domain subdomains are polygonal domains. This is in this context take a boundary, small boundary. Okay. The procedure of this method. Okay, we consider the coefficient high contrast in this form. Eta is very higher of the high conductivity. We then consider previous work by Victor Carlo and Galvis about asymptotic expansion for high contrast coefficients in elliptic equations. We consider this solution in particular. This is asymptotic expansion in this case. Here we have this is boundary conditions. Again, U0 in the first terms of the expansion takes this condition in the boundary, and other terms take this is equal to 0 in the boundary of G. Okay, the process is basically take a weak formulation for this problem. Okay, he replaced the solution in this eta, this solution here, and again write this function and u jota for jota equals 0 to 1. This is satisfying the condition of the boundary. Okay, put in this case is omega equal to union of dm, and calculate this equation here. We obtain the equation here, and machine powers. We have these three equations or system. In these cases, we consider principally this function for our work. Okay, the application of this method is the limit term U0 is important for applications. It offers approximation of U eta for high contrast problems. U0 is the constants inside inclusion. It's a conclusion of the previous work. But computing the right value of the constants is important to design numerical procedures. Having a practical process to compute the next leading other terms and useful for applications. For example, the velocity. It's very simple. Computation is effective properties for energies. Okay. The high order expansion is also useful when construct the multi-scale and multi-level methods. This is the work. The expansion can be used to construct the multi-scale finite element method. This is the how we're talking about. this. Okay. Well, the previous word, we take the convergence of the method. We consider of this asymptotic expansion. We conclude that the method is convergence of this case. Okay, the description of the method. We take a harmonic characteristic function in this form. Okay, we usually take one inclusion and declare. We have the extension for this function in the future. Well, okay, the asymptotic limit u0, we obtain this form for first term of the expansion, where chi dm are the harmonic characteristic functions, this, and u00 satisfy this simple problem in the d0 in the background of the problem. Okay, the idea is calculate these constants. Okay, put C on the vector form in the Rm. Then C satisfies the linear systems, where A is a geometric stiffness matrix. A jump has all information about the geometry of the domain in these cases. And okay, we'll consider these. Okay, in this case we consider, for simplicity of the function test is equal to characteristic function. And the B, you have this form. Okay. Again, you calculate another terms of the expansion. You have this process. J is computed in two steps. Solve the Newman problem in each inclusion with data from width uj minus 1, and solve the Dirichlet problem in the background d0 with data in each inclusion. And the constants in this part are computed solving a linear system similar to the one before. Okay, the example is we consider G and the circle with center in 0, 0, radius 1, and we consider 36 identical circular inclusion of radius 0.07 with eta equals 6 in this case. F is equal 1, and the boundary condition is the polynomial function in this case. Here we have geometry on the meshes in these cases. Here we have the finite element solutions for this problem. In this design is the U0 in this domain. And okay, we consider that the composition of U0. First, here the U00 in the background. This is the solution in this part, and consider this other part of U0. This is the solution. Okay, we compute another terms, a few terms. In this case is U1. the behavior of the background, the behavior of the inclusions, the same of U2. Okay. The approximation, the localized harmonic characteristic function introduces again the localized harmonic characteristic functions, where the constant function is each inclusion to extend it harmonically only on a neighborhood of the expansion. In these cases, we consider the neighborhood in this condition. Take the harmonic characteristic function in this form. In these cases, we take a neighborhood in these inclusions, and we study the behavior in this case. Okay, the solution is replace the harmonic characteristic function, the original characteristic function, replaced to new characteristic function, restricting to the neighborhood. In these cases, take the U0 for simplicity of the presentation. We take only U0. In these cases, solves U0 in terms of the neighborhood, in this case. And we use the A delta, again the stiffness matrix, instead of this. The numerical results, okay, they take the illustration of truncation error. In these cases, the error is a relative error in the Sobolev norm, essentially. Okay. The error in U0, okay, take different values of delta. Here the relative error in the U0 and U0 localized, you take this form, okay? Here we consider U00 in these cases, and UZ is the part of the inclusions only. Okay. And the second example is to this. Okay, again the same thing, and the 60 identical circular inclusions in this case with same value of eta and this same condition to develop. Okay, this is the table of the solution. The different delta here. Okay. Anyway, ongoing work. For this work, we can try to. We try to understand the analysis, numerical analysis of the method, and we have to study decay of the harmonic characteristic function, or more details of this problem. We considered, in this case, linear elasticity, detail of the study of A geometrics and interaction among inclusion. About this part, we have previous work, only the one inclusion. Okay. Yeah, we'll study another equation, for example, the heat wave, nonlinear, for for this method. Okay. The main reference here is the asymptotic expansions for high contrast elliptic equation. This is, you find the results, the solve of the asymptotic problems. In this one, okay, maybe, thanks, sorry.